Guys, welcome back to chapter 19. What we're going to do now is we're going to apply what we've learned in electrochemistry to useful scenarios. So we're going to make things out of our redox reactions. Okay. So first thing we need to talk about is Voltaic cells. So Voltaic cells is something that that produces a current. And it produces a current or produces a flow of electrons from a spontaneous redox reaction. So inside of this cell, we've got a spontaneous reaction. That reaction is a redox reaction, so electrons are flowing. And if we close this circuit up, we can make what's called a Voltaic cell. So electrical current is officially defined as the flow of electrons. So what kinds of reactions will result from the transfer of electrons from one substance to another? Well, redox reactions, right? Of course. So a redox reaction or oxidation reduction reaction causes electrons to transfer from one substance to another. Okay, so here's a redox reaction. We got solid zinc reacts with copper that's dissolved in solution, and it's going to produce zinc that's dissolved in solution and a solid piece of copper. Okay. Well, what if we separated these two reactions? Okay, instead of one big reaction all happening in the same beaker, what if we took the two half reactions and put them into their own beakers? So a beaker with zinc and a beaker with copper. And then maybe we connected those two beakers with a wire. Yeah, something that electrons could flow through. And then in the middle of that wire, we could put something that it could do work on, like a meter or a light bulb or anything really, right? So that's a Voltaic cell. That's exactly what we do with a Voltaic cell. So what you'll see here is our first half reaction. So here is our beaker. Inside of the beaker, we've got aqueous solution. So this is aqueous zinc nitrate. In this case, nitrate is just our spectator. Zinc is obviously what we're interested in. So we've got aqueous zinc in here. And then this guy right here is literally a solid piece of zinc that is just submerged into that liquid. Okay, so our solid piece of zinc and our aqueous zinc in that beaker. And in this beaker over here, we've got our other half reaction. So we've got our copper nitrate, so our aqueous copper. And then our solid piece of copper literally submerged into that liquid. So we've got our aqueous copper and we've got our solid piece of copper. And we have connected those two half reactions because we know they're going to transfer electrons, right? Somebody's going to lose, somebody's going to gain. We connected those two half reactions with a wire. So something that will allow the electrons to flow from one side of the reaction to the other. So we can flow with those electrons. Okay. So here's our Voltaic cell. Half redox reaction, something that connects the two that allows the electrons to flow. Okay. So some terminology that we need to get out of the way. Voltaic cell. So a Voltaic cell is an electrochemical cell that produces an electrical current. Electrochemical cell. Chemical, we're chemists. We're studying a chemical reaction. Electro, electrons are going to be moving. And then the cell just kind of tells us that this is a closed circuit, a closed system. So a chemical reaction in a closed system that produces some flowing electrons. That's a Voltaic cell. Half cell. Half cell is where each of the half redox reactions happen. So this beaker is a half cell, and this beaker is a half cell. So it's where the half redox happens. Cathode is going to be where the reduction takes place. Anode is going to be where the oxidation takes place. Okay? So anode oxidation loses electrons oxidized. So our anode is going to be where electrons escape, where we lose our electrons. Okay? So anode is going to be where our oxidation takes place, losing electrons. Cathode is going to be our reduction. So gain electrons reduced. So our cathode is going to be where the electrons congregate, where they come together. Okay? So electrodes, kind of the broad umbrella that these fall under, we call them electrodes. That's going to be just the surface where electrons can enter or leave the half cell. So it's got to go to the surface and leave, or it's got to go surface and enter. So that's what the purpose of an electrode is. The surface where they leave is the anode. The surface where they congregate or enter, come in, is the cathode. Anodes tend to be negatively charged, so electrons will go away from negative. Remember, they transfer negative to positive, so they will be repelled by the negative and attracted to the positive. And then the last thing in this picture that we haven't talked about yet is the salt bridge. I am not going to get into too much detail about the salt bridge. But if you think about electrons going from, in this case, left to right, left to right, left to right, left to right, you can see that the charge over here is going to have a buildup of negative ions, and the charge over here is going to have a buildup of positive ions. If we do not have a salt bridge, the life of this voltaic cell will be very, very short. So once it starts to build up that really big potential between the two, electrons are going to stop flowing at some point or slow down. This salt bridge allows spectator ions to flow back and forth just to neutralize each of those solutions. So as the electrons exit, some of this nitrate comes in to replace that negative charge that it lost. And as electrons enter, some positively charged ions come in to neutralize that out. So it's just a pathway for counter ions. Okay. All right, so here is our voltaic cell. So we've talked about what a voltaic cell is. We've talked about each of the half cells. We've talked about that it goes from anode to cathode. Electrons travel negative to positive. And I forgot to mention this before. So we go anode to cathode. So again, electrons flow alphabetically. So A to C, anode to cathode. And then we talked about our salt bridge. Okay. So why is zinc the anode? And why is copper the cathode? What we'll see in probably the next lecture is that zinc has a higher potential energy. It will ionize more readily than the copper. High potential energy, unstable, will travel to lower potential energy, more stable. Okay, so nothing new here. High potential to low potential. So anode, high potential, to cathode, low potential. And we'll put numbers to that in just a second. But and here's the picture of what's going on. This is actually really important. So what is going on in each of these half cells? So I told you that electrons are transferred. I told you that the electrode is the substance by which it transfers. But what is actually happening? So what we see here is that zinc with the higher potential energy more readily will ionize. So what does that mean by it will more readily ionize? This zinc will pop off of this anode. So this solid zinc pops off of the anode and it will dissolve into solution. To do that, popping off, dissolving into solution, it has to be an ion when it dissolves in solution. So what it does is it kicks off his 2 electrons, bink, bink, and sends them through the wire. So he's going to kick off 2 electrons, send them through the wire. He is now a positively charged ion, and he is now dissolved in solution. That's the oxidation. Lose electrons, oxidize, solid zinc will kick away 2 electrons, and it will dissolve in solution. Those electrons will transfer through our wire and will come into contact with the cathode. When those electrons enter into this solution, those electrons will be attracted to the copper that is dissolved in solution. So those electrons will jump onto an ion of copper and say, come here, I want to neutralize you. So this guy will gain those 2 electrons. No longer is he going to be soluble in water, so gain 2 electrons, and bam, he will add to this metal cathode here. Okay. So over time, what we will see is that this anode will get smaller and smaller and smaller and smaller as the zinc pops off and dissolves in solution. And this cathode will get bigger and bigger and bigger as the copper that's in solution attaches to this cathode. Okay, so that we will see that happen. So that is what happens on the molecular level during in a voltaic cell, I should say. So what I want you guys to do now is I want you to pause the video and I want you guys to think about where everything would be in the voltaic cell. So if a voltaic cell is based on the reaction above, indicate the electrodes, the salt bridges, and then where each of the chemicals will be in the picture. Go ahead and assume that this chemical reaction is in the same direction as this electrons flowing. So the chemical reaction is going to flow from left to right, and electrons are going to flow from left to right. So go ahead and draw this scenario. All right, so first thing I'm going to do is just do our 2 half reactions. So the first half reaction I see, we've got manganese as a 2+ ion, and it's going to eventually become manganese as a solid. Okay. So oxidation-wise, we go from a +2 to a 0. So that number is getting bigger. That is going to be, that number is getting smaller. That's going to be our reduction. Okay. And then we see that we've got lead as a solid is going to become lead as an ion. So we're going to go from a 0 to a +1. That number gets bigger. So that's going to be our oxidation. Okay. All right. So electrons are going to flow from oxidation to reduction, or from anode to cathode. Okay. So lead is going to be our anode. So this piece of metal right here is going to be our solid lead. And down here in solution is going to be where we find our aqueous lead. Okay. So it's going to have some sort of counter ion down there. I didn't give you any indication what that counter ion is. So just know that the aqueous lead is what's in this beaker here. On our reduction side, so this is going to be our solid piece of manganese right here. And in solution is going to be our aqueous manganese, like that. Okay. This is our anode. This is our cathode. We're flowing negative to positive. And then the last thing that I'd like to, I didn't ask you to do this, but the last thing that I'd like to talk about is the fact that this is the salt bridge. Okay, so that's what that is right there. So there's our Voltaic cell. We put it together into two half reactions, determine the oxidation at our anode, reduction at our cathode. I hope you guys found this helpful.